Imagine writing, I timed the pendulum and calculated density. Sounds perfectly fine in your head, right? Well, that answer gets exactly 0 method marks. Now imagine writing, measured 10 oscillations, t equals 1.2 seconds, calculated density using mass over volume to 2 sig figs. Bam, full marks. In this explainer, we're going to take those average, completely invisible mark-losing habits and transform them into top-band A-grade Cambridge responses.
Okay, let's actually dive into this before and after shock because it's a huge deal. That first answer, I timed the pendulum and calculated density, it feels like a completely normal sentence to write. But to a Cambridge examiner, it is an absolute disaster. It doesn't tell them anything. But that second response, measured 10 oscillations, t equals 1.2 seconds, calculated density to 2 sig figs. That perfectly fulfills the mark scheme. It gives the exact variable measured, the unit, the actual formula used, and the precision. That right there, that tiny shift in wording, is literally the difference between just passing and absolutely excelling.
You know, the stakes here are massive. There are these incredibly common mistakes that just act like absolute grade destroyers. I'm talking about leaving your units off entirely, rounding your numbers way too early in the middle of a calculation, just throwing down vague explanations. Or what about mixing up your graph axes? That instantly ruins our gradient calculation. Or writing a conclusion that your very own data table doesn't even support. It is so rarely a lack of physics knowledge that hurts students. It's almost always a lack of practical exam technique. These simple, silly errors just bleed away marks one by one until your grade boundary completely vanishes. And honestly, this is exactly why ordinary revision completely fails for the practical paper. You can sit in your room and memorize every single equation in the 0625 syllabus until you're blue in the face, but that doesn't teach you how to handle unpredictable apparatus in a live laboratory setting. Like, what do you do with a sticky micrometer or a wobbly retort stand? Just reading the textbook doesn't show you how to design a proper data table from scratch or how to evaluate the reliability of a swinging pendulum. Examiners don't just want to know that you memorize the theory. They want to see practical, real-world data handling. Now, in just a second, I am going to show you the exact examiner safety check that literally flips a practical evaluation from a straight fail to a top band mark. It is a clue that completely changes how you write your answers. But first, you absolutely need the framework that makes that clue incredibly obvious. Because if you miss this framework, that examiner clue isn't going to make any sense at all. So here is the secret. It's a 4-step high-mark framework, and you need to use this to structure every single practical answer. Step 1, the concept. What are you actually measuring? Step 2, the evidence or data. We are talking hard numbers with units here. Step 3 is scientific reasoning. Why did you take the measurement that specific way? And finally, step 4, examiner wording. This means using the exact vocabulary the Cambridge mark scheme is looking for. Let's see what happens when we actually put this into practice. Think about some flawed, lazy data for a minute. Writing something like length equals 4. Well, for what? Meters? Millimeters? Bananas? You can't do that. Compare that to top band data. Length equals 4.0 centimeters. It has a unit, and it's written to one decimal place to show the actual precision of the ruler. Or look at volume. You can't leave it as 12.333. You have to round it down to 12.3 centimeters cubed based on your instrument's precision. And density. You absolutely cannot just describe it as fast or high. You need a cold, hard, calculated value like 3.1 grams per centimeter cubed. Refusing to round too early and writing precise units, that is your ironclad evidence. Now let's level up and apply this framework to graphing. Writing graph of length and time is just way too vague. Which one goes on the y-axis? What are the units? You're practically giving away marks. Instead, use exact examiner wording. Write y-axis, time, /s, x-axis, length, /m. You always state the variable, use a slash, and then the unit. Plus, you have to ensure it's properly scaled to cover more than half the graph paper. That is exactly how you lock in those graphing marks. All right, so we've got data representation down. Now, let's test your real-world lab awareness. Pause and predict for a second. Can you spot the specific safety error in connecting a live, high-output electrical circuit right next to a wet laboratory sink? Sure, it sounds obvious, but how exactly do you write this down to get the evaluation mark in the exam? What specific wording is that examiner hunting for? If your answer was just, well, it's dangerous, you get 0. Seriously. Here is the exact text pulled straight from the examiner's manual. Turn off the power. When connecting electrical circuits, ensure the power is turned off. When you are ready to take measurements, check the circuit and set the power to a low output before turning it on. And obviously keep circuits far away from water to avoid electric shocks that can cause burns or completely fry sensitive meters. You must write down the specific action and specific hazard to secure that mark. Let's escalate things a bit with another spot the error challenge. Think about this. What is the specific hazard of leaving a mercury thermometer rolling loosely on a high laboratory bench? Once again, writing "it might break" is not going to get you the top mark. What is the actual physics or chemical hazard we are worried about here?
And this perfectly illustrates those hidden safety marks scattered throughout the 0625 syllabus. The real issue with that thermometer isn't just broken glass, it's that mercury is highly toxic. You literally have to explicitly state, "take care with toxic mercury." Look at the rest of these guaranteed method marks. Set hot liquids in a safe position to avoid burns. Protect your eyes from lasers or ultraviolet radiation. Always wear shoes to protect your feet from heavy falling weights. Tie back long hair so it doesn't catch fire in a flame. You really need to memorize these specific actions and hazards.
So let's bring this all together. To truly master the practical paper, you've got to pair your concept, your evidence, and your scientific reasoning directly with this exact safety protocol wording. Whenever a question asks you to evaluate an experiment or suggest improvements, combining your structured data handling with precise examiner-approved safety knowledge is what absolutely locks in those top-end marks. It's a game changer. But here is the truly terrifying part. You could have the perfect framework, a flawless data table, perfect safety protocols, but what if you're answering the completely wrong question? What if the exam tells you to evaluate something, but your answer only describes it? Misinterpreting those command words will instantly cap your grade, and it won't matter how good your underlying physics is.
You literally cannot afford to let command words ruin your perfect framework. Understanding the absolute difference between explain, describe, and evaluate is the absolute mandatory next step to securing your A grade. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations, and jump straight into our next explainer where we completely decode the command words that decide your final mark band. We are going to show you how to transform a whole paragraph of waffling text into one concise A grade evaluation. You don't want to miss it. See you over there.